This topic is all about work done.
Work done. Okay? And if you want to measure work done, at its very basic, there are two scenarios. There's a scenario where you are moving something horizontally, and you are using a force to do that. And so the work done is the force times the distance. And you'll know from physics, some of you anyway, that we tend to use S for distance. And that is work done, which is measured in joules. Joules is the metric unit, the imperial unit of work done is the calorie, and we're still very much in this country, aren't we, tied to calories, you know, 250 calories in a Mars bar.
And if we are moving something vertically, then we are moving it against gravity. So in
vertical movement,
we've got something which has a mass, then effectively the force that is involved in that is the force pulling it down, which is the mass times the acceleration to gravity, mg.
Now I'm assuming is that from GCSE? Is that so? If something has a mass of 2 kilograms, it has a weight of 2 times 9.8 in maths, 9.81 in physics. So the work done, if you move it up, is mass times acceleration due to gravity, 9.8, that's a constant, times the distance. And that tends to be abbreviated mgh, so m for mass, g, and then h for distance, because it's being moved up. Again, measured in joules. So at its very basic, that is what work involves. But questions involving work involve much more than just that. So that's why we need to do a little bit of background work in order to go any further.
So, I want to tell you about Isaac Newton. Okay? So, he was a very clever guy. And he's famous for a number of things, not just for sitting under an apple tree. But he is famous in this context for his 3 laws, which are about sort of motion and force and acceleration. And Newton's first law basically says if something doesn't get shoved, it doesn't move. That's basically my interpretation of it. Okay? If you don't shove something, it doesn't move. Now that's not quite as complicated as it gets, but basically if you've got an object which is stationary and you don't apply a force, it's going to stay stationary. So let's pretend we've got
a mass here of 5 kilograms. There are actually forces involved there.
That block has a weight of 5 times 9.85 g.
And because it doesn't collapse through the floor, it means the floor is pushing upwards with a force that's called the reaction force. And those two forces are equal. They have to be. They have to be. If they're not equal, then that's when floors collapse. If the mass of the object is more than the reaction force, then the floor can put up. And I'm always really amazed at how clever floors are. Because
the floor is only pushing up with exactly the mass, the weight that it needs to equalise my weight. How does it know? How does it know? You know, I might have eaten a few too many,
package of crisps over the weekend. I might be a little heavier than I was yesterday. It still knows. It still knows. The force that the floor applies to me is exactly the same as the force that the floor is applying down.
But those forces are balanced, so there's going to be no change in the movement. It's in equilibrium. It's not moving. And the same is true if something is moving with a constant velocity. So let's say something is moving with a velocity of 2 meters per second. It's being pulled by a force, and like most things, there's a friction. So I'm going to use P for that. There's a friction force holding it back. But let's say these two are exactly the same. which is what my car needs to do if I'm going to maintain constant speed. The energy, the force that my engine is producing needs to exactly match the friction that's holding it back. Any more than that, and I accelerate, any less than that, I decelerate. If things are going to be constant, then that force needs to be exactly the same. We've still got downward weight, and we've still got the reaction force, but everything is balanced. So Newton's first law says things remain in equilibrium, either stationary or with a constant velocity, unless they're acted on by an unbalanced force. No unbalanced force there. So, for example 1, it's going to stay stationary. Example 2, it's going to stay at its constant velocity. That was Newton's first law. Newton's second law
Would anyone like to guess what my simplification of Newton's second law is? If you shove something, it's going to accelerate. Okay, that's what Newton's second law says. As soon as a force is unbalanced, it's going to accelerate. And so if we have this 5 kilogram weight and we're pulling it, there's a friction force. We've still got
the reaction force, which is exactly the same as that force. But let's say we increase P, so it's more than the friction force. That's no longer a balanced force. And so what we're going to get in that situation is an acceleration. It won't stay constant, it's going to accelerate. And Newton's second law was that acceleration is proportional to the net force. Okay, so the net force, if it's moving in that direction, is that, take away that. It's proportional to the net force. So if that net force is greater, then the acceleration is greater. It's inversely proportional to the mass. So if it's heavier, the acceleration will be less. So we can say it's multiplied by the force divided by the mass, and that formula is nearly always stated like this, F equals ma. So that's the force, and that force stands for the overall resultant force. The force moving in one direction minus force moving in the other creates an acceleration, and that formula, force equals mass acceleration, summarises that.
Yes. Okay. So, for example, let us say that, and my apologies to those of you that you've got a 5 kilogram weight. It experiences friction equal to 3 newtons. It's being pulled by a force of 10 newtons. We start from scratch, so we start from 0. What I'd like to know is the size of the reaction force. I'd like to know the size of the acceleration it will experience, and therefore how fast will it be going after 3 seconds. So I want to know the size of r, I want to know the acceleration it's going to experience, and because it's unbalanced, it's going to be accelerating in that direction, and therefore I want to know how far it will be going, how fast it will be going after 3 seconds. So a quick go at that. Okay. So Goldthurston, in terms of G, give me the size of the reaction force. 5G. 5G. Yeah. So the reaction force is the force that exactly matches the weight of the object. So if it's 5 kilograms, it will have a weight of 50-ish newtons, 5 times 9.8 or 5 times 9.81. And the reaction force, the force the floor pushes up on it, is exactly the same. So Tristan, are we in a first law or a second law situation?
Second law.
We are, because we've got an unbalanced force. First law says if the forces are balanced, nothing's going to change. It'll either stay still or it'll stay at its constant velocity. Here we've got unbalanced forces. We haven't got an unbalanced force vertically, which is why it's not going to move off the floor. But we do have an unbalanced force in this direction. So if we resolve in that direction, that's a notation that I tend to use in maths. Do I use that in physics? No? What do you say when you're thinking about something horizontally rolling vertically? So resolving vertically, because we're dealing with a second law situation, I'm going to consider my F equals ma formula. So I'm not interested in these forces at all, because these forces are acting at right angles. They're not going to make any change to the movement in this direction, and that's the only direction I'm interested in. So Jake, what's the net force? If I'm thinking about that direction there, I've got some forces going in that direction, but I've also got some forces going in that direction. 7, yeah, brilliant, yeah. So the net force is 7, isn't it? That's the unbalanced force. That's Newton's unbalanced force, and that equals 5, which is the mass, times the acceleration. So the acceleration is 1.4 meters per second squared. So Jack, it started from 0. How fast will it be going after 3 seconds? 4.2. Yeah, and we can use our Suvat equations or we can use common sense. This acceleration means that every second it gets 1.4 meters per second faster. So after 1 second it will go at 1.4, after 2 seconds it will go at 2.8, after 3 seconds it will go at 4.7. Okay, so we've got Newton's first law and Newton's second law. But that's all nice and simple if everything's in horizontal or vertical. So let's then look at what happens if we've got something on a horizontal surface, he says. He draws a downhill surface. It's supposed to be horizontal. And this time I want you to imagine that surface is smooth. So there is no friction involved at all. Now that's an assumption which is never true, but it helps sometimes to make calculations a bit easier. And if the surface is pretty skiddy, then it's a safe assumption to make. Let's say we've got a 12 kilogram mass, and we're pulling it with a force, but that force is going up at an angle. We're pulling it with a 40 Newton force. And that force is going up an angle, and let's say the angle is an angle of 15 degrees. Have you done this in physics? I do it differently. Well, no, I don't. That 40 Newton force at an angle throws us a proper curveball, because it has an effect both horizontally and vertically. It's going at an angle, so it's having a slight effect in an upwards direction and a pretty big effect in a horizontal direction. And so we've got to consider it in both those situations. So let's start by thinking horizontally. And what we can do is as simple as this. We can say, okay, let's draw a sort of force diagram for what's going on there. The effect of that 40 Newton force in a horizontal direction will be equal to the length of that line there. So if this force is 40, the hypotenuse, and I want to know the adjacent, hypotenuse adjacent is cos. So I know that the cos of 15 will be adjacent over hypotenuse. And so that means the size of that force in a horizontal direction will be 40 times the cos of 15. And we call that the horizontal component of that force. So it's the effect of that 40 Newton force in that direction. And it's always going to be the same. It's always the size multiplied by the cos of the angle. So we're dealing here with a single force acting horizontally, no friction this time. So that's 40 times the cos of 15. And I want to know the acceleration. So that's mass times acceleration. Go on, just quickly humour me and work out the acceleration of that one for me. And we default to 3 significant figures. Sorry, no we don't. No we don't, sorry. We default with mechanics to 2 significant figures, but I think that's just why we default to mechanics to 2 significant figures, whereas everywhere else in A-level maths we default to 3 significant figures. We tend to use 9.8 as our value of G, which is a 2 significant figure value. So yeah, so we go to 2 significant figures. Now, while we're here, let's calculate the size of the reaction force. Okay? Remember, the reaction force is the force acting up, and it is nearly always exactly the same as the force acting down, which in this case will be 12G. But don't forget, the spanner in the works is that we've got this 40 Newton force, which will also have a bit of an upwards effect. Now, resolving horizontally was a Newton's second law problem. Okay. Frank, what is going to be, which of the laws are we going to be used when we're resolving vertically?
First law.
Yeah, because it's not moving up or down. It's still in equilibrium. You know, you don't, if you apply a force to at an angle to a block like that, it's not going to levitate. You know, it's not going to levitate. So when we deal with our vertical forces in this situation, we're back to Newton's first law, which is basically telling us that in this case, up equals down. The forces up must equal the forces down. We've got one force down, 12G. We've got 2 forces up. We've got R, and we've got the vertical component of that force. Now, this is where I differ from my physics colleagues, but it's only because I'm not that bright. I say, okay, I'm going to do exactly the same as I did here for this force. So I'm going to say, right, that's 40, that angle there is 75. So I'm going to say that that force there is 40 times the cos of 75. I'm assuming you say 40 times the sine of 15. Yeah. So it's the same. It's
exactly the same. So we've got R plus 40 times the cos of 75. I just like this idea that when you're working out a resultant force, it's the force multiplied by the cos of the angle involved. So that was 40 cos 15, that's 40 cos 75. Now, I don't know how Mrs. Clark and Mr. Caffrey do it, so I apologise if I'm, but you know, it's the same thing. So you just want to work out in that case the size of R. How big R is in that case.
Oh, I've just rubbed it out. What an idiot. So are you all doing physics apart from Jay? And B. B isn't doing either. Oh, really? Is she? I don't think she's doing it. So we use 9.8, go figure. I mean, you're never going to lose marks from being more accurate than you need to. So it's interesting, this one, isn't it? I mean, you get 107, which, you know, you think, well, should I really round that to two significant figures? So I think I do my usual thing of sort of writing it like that, and then putting it like that, just to sort of cover my bases. But, okay. Now, I apologise that was all a little bit rushed, but let's now see if we can apply that to questions which involve work done. Which, remember, yes, sorry.
I was going to say, so would that only work up to a point? If the pulling force is big enough, then it would go off the ground.
Yeah, eventually, a force at that distance, at that angle, would.
So is it if the vertical component was greater than the weight?
Yes, yeah. I suppose if yes, that's right, isn't it? Yes, yes. I guess it's that's right. It will leave the ground when R falls to 0, won't it?
Well, that's a really good point. I because this always comes up, and I always get a nice clear answer to it, and I can't remember what it was last time.
I think using 9.81 instead of 9.8 is fine. What your bigger problem would be is if in physics you use 9.8 to 9.81. So that's the problem. But it does say on the front of the maths exam that use 9.8. So I guess they could keep roughly about it. Right, shall we do some? Let's do some actual sums then, which involve work. So. I regret not thinking this now, but there we go. Let's see how much we can see. So we are on page 18 in the textbook for those at home. Does Rory do? So I reckon that
it's worth doing just a few of these questions. Can you see those questions? Can you see those questions? So if we just do that one, and just do that one, and then that one, and 7 and 8, but 8 you can't see, so we'll scroll up once we've done that one. Okay? So 1 and 3 are just plugging numbers into the formula. And remember, the units of work done are joules. For some reason, my mum gets notifications when I upload my lesson video. So, hello, Mum. Joules. I know it's a very nice brand of clothing, but it's also the units for work done. Okay. So if we're talking about horizontal movement, it's just force times distance. If we're talking about vertical movement, then it's mass, so the mass of whatever it is, times g, which is 9.8, times how far it is moving. Oh. Yeah, do you know what? I think that two-thing thing of rounding is only if you've got something that goes on ridiculously. I'm not going to round 2.5. Actually, interestingly, I can check this, can't I? So, what do they do? They use 2.5. Yeah. So I think that rounding 2 centimetres is only if you've got a long and silly answer. So for question 5, the box, I've got to consider, is this a Newton's first law or a Newton's second law situation?
So what do you reckon, Ben? First law or second law situation?
First law.
First law, constant speed. So that means everything's balanced. So the force pulling it will be 22 newtons. The force pulling it will be 22 newtons. Now, when we use this formula, this isn't the resultant force. This is the force, the effort we're putting in. That's the work we're putting in. So the force pulling it will have to be 22 newtons as well. So the work done in question 5, and it's being pushed rather than pulled, but it's the same thing, would be 15 times 22. 15 times 22, that tells you how many joules. Can I scroll at that point? Because question 8's a real good one. So question 8, you've got a, so I think it's worth doing. It's interesting, this idea about the work done by gravity rather than the work done by... Okay, so the ball falling 15 metres from rest, we're not doing any work, but there is work being done, and that's gravity. So it's it's 0.5 times 9.8 times 15. That's the work done by gravity. And you some of you will realise that within any system energy is conserved. Well, that energy was put into it by lifting it in the first place. So we've got this whole concept of sort of potential energy, which we get into. So here we've got like a backwards question. So we've got the work done is 30 kilojoules, so that's 30,000 joules. So we've got mgh equals 30,000 30,000. The mass is 80. So the height is 30,000 divided by that, which comes out as and they're using 3 significant figures there. Yeah, I'm absolutely sure on this. Mark schemes always use 2 significant figures when it needs rounding like that. And this is an interesting one, this question 8. I mean, we're only asked about the work done, which is force times distance. You could say, well, you know, if I'm pulling this, I'm putting 18 newtons of force in. But we still use the horizontal component of the force. So the work done in question 8 is still 18 cos 25. That's the resultant force in that direction, multiplied by the distance, which is 14 metres. And then the modelling assumption, well, when you get a question like that, you've got to look in the question for a word that implies we've made an assumption, and that word is here. So we have assumed that there is no friction involved. We have assumed there is no friction involved. So that gives us that. And I've run out of time, but friction is where I want to go next, really. I think friction is fascinating. A little bit like, how does the floor know how much force to put up? When I push something, and you know me, I'm quite hench, you know, and so I have no trouble pushing things like this. But if I push this as hard as I can, if it doesn't move, that's because friction's resisting me. But it's resisting me with the force exactly the same as the force I'm applying. How does it know? How does it know what force I'm going to apply? And then it reaches a point where it goes, hang on a minute, no, I'm out, and it starts to move. So why is that? You know, why is that? We'll talk about that next lesson. I can hardly wait. Now, the work I had intended for you to do independently was after friction. So there you go. If you happen to look at that discrete paper I've sent you, do that as your independent stuff this week.